A warning sign is suspended by means of two light inextendable struts from a pole next to a highway. Strut A makes an angle of 30 degrees with the horizontal strut B, which makes an angle of 90 degrees with the pole. The mass of the sign is 10 kilograms. Well, obviously there's a weight acting down over here. You want to put it into a sketch diagram. In essence, this thing would just hang straight down. There would be a tension in this rope away from, and then you've got strut B, which is pushing towards the right. And then you've got the weight acting downwards. So I'm going to bring in my weight. I'm going to put in strut B at 90 degrees. Then at 30 degrees, I'm going to put in strut A. And that's going to be 30 degrees over there. So in essence, I've picked up those three forces and I have put them into a closed triangle. I can put them into a closed triangle because of the fact that they are all in equilibrium. So it's all balanced, and that's the picture. So now we need to calculate the magnitude of the tension in strut A. So that is your hypotenuse. You're told that the sign is 10 kilograms, so let's get the weight of that sign. It's 10 times 9,8, which is going to be 98 newtons. And now if I'm trying to find, based on what I've been given, which is this angle of 30 degrees here, that's opposite, that's hypotenuse, that's adjacent. So I'm going to say I'm interested in the hypotenuse, I know the opposite, so sine of 30 degrees is equal to the opposite, which is 98, over the hypotenuse that I do not know. The hypotenuse is therefore equal to, I pop that into a little triangle, 98 is at the top, and sine 30 is at the bottom. And what comes out of there is that A is equal to 196 newtons. Then it says calculate the compression in strut B. Now I'm going to be looking at the adjacent side. I know the opposite side. So I'm going to say tan of 30 degrees is equal to my opposite side, which is 98, over my adjacent side, which is strut B. I can then again do this triangle technique, and I can say B is equal to 98 over tan 30 degrees, and I find that B turns out to be 169,74 newtons. Malcolm Campbell and his Bluebird set a world land speed record of 280 kilometers per hour. The current holder of the record is the Thrust SCC, a jet-powered car which achieved 127 kilometers per hour, and the Bloodhound will go to Haskeen Pan in the Northern Cape to try and break the record. He will need to prepare an 18-kilometer long and 1,500 meter wide, about 40 times the size of Campbell's. That must be flat, there must be no stones on it or anything like that. The Bloodhound team will need to load about 400 kilograms of jet fuel and a ton of high-test peroxide to reach the speed of 160 kilometers per hour from rest in only 42 seconds. Our first job is to convert 1,600 kilometers per hour, which into meters per second. So it's going to be 1,600, 1,000. I put another 3 noughts on to get to meters, and then I have got kilometers per hour. So it was 1,600 kilometers per 1 hour. I need to convert an hour into seconds. It's 3,600. 60 times 60, and that is equal to 444,44 meters per second. That's very fast for a car to go. Nearly 500 meters in a second, half kilometer. Calculate the magnitude of the acceleration of this Bloodhound. So I have got, it starts at rest, I've got a final velocity, and I've got a time of 42 seconds. So V is equal to U plus AT, which is equal to, I put sub in 444 if you like, 0 plus, I don't know the acceleration, but I do know the time is 42 seconds. My acceleration is 10,58 meters per second squared. How far does the Bloodhound travel in 42 seconds? So I take the same information over here, and I now use my equation of motion. S is equal to U plus V divided by 2T. Substitute in 444,44 plus 0. over 2 multiplied by 42, and my distance turns out to be 9,333,24 meters. The bloodhound will stay at this top speed for 10 seconds and then deploy its parachute to bring it to rest before the 18-kilometer mark. It's already gone 9 kilometers, hey? Calculate the minimum deceleration of the bloodhound under these conditions. The first thing I need to do is I need to see him staying at the top speed for 10 seconds. So how are we going to do that? We are going to say constant velocity, S is equal to V times T, 444,44, multiplied by 10 seconds, and I will have covered 4,444,4 meters. So, this bloodhound started, it went 9,333,24, it's now gone 4,444,4, and therefore, and altogether I have got 18,000 meters, that's 18 kilometers, minus the accelerating part of the journey, minus the constant velocity part of the journey, and what's left is a distance of 4,222,36 meters that he will need to go for. Over that distance, he will have started at, because bear in mind he was going at this constant velocity over here, so he's going to start at this 4,440, and he's going to end at 0 because he's going to come to rest. So we can go v squared is equal to u squared plus 2as, ends at 0, starts at 444,44, plus 2, I don't know his deceleration, but I do know the distance that he's got left to decelerate, and that is going to be 4,222,36. When I resolve all of that, my acceleration becomes slowing down at 23,39 meters per second squared. Good thing he's got a parachute coming out the back there. Then it says I have to sketch a velocity time graph for the complete journey, and I need to include any key values that I already have. So what am I going to do? First thing I suppose is I'm going to label my velocity time graph. So I'm going to go velocity time. I know I've got 42 seconds, then 10 seconds, and I don't know the last little bit of time. I do know that in those first 42 seconds I get up to a velocity of 444. I then stay at that constant velocity for another 10 seconds. Remember, this is a velocity time graph. And finally I slow down again, and I don't have key values for that, so I'm just going to show that I slow down back down to 0. A new method of pizza delivery to high-rise buildings is by a drone carrier. The drone holding the pizza moves vertically upwards at a constant velocity. On a test run, the drone accidentally releases the pizza from a height of 5 meters above the ground. Remember to assign directions carefully when answering this question. Calculate the speed at which the box hits the ground. The first thing is that we need to recognize that this box started at 3 meters per second upwards. That was its original velocity. It then traveled a distance of 5 meters just before it hit the ground. And I don't know the final velocity, but I do know that in free fall, its acceleration, this was up, this is down, and it's 9,8 meters per second squared downwards. And then I say v squared equals u squared plus 2as. And the final velocity is going to be plus 3. I'm going to take up as positive, plus 2 minus 9,8 because that's down, minus 5 because that's down, and I find that my v turns out to be 10,34 meters per second. It asked me for the speed, so I shouldn't give a direction at all because speed is a scalar quantity. Calculate the time taken from the moment it is released until it hits the ground. So I use exactly the same data, but this time I put it into v is equal to u plus at, and that is my final velocity is minus going downwards 10,34. My initial was going up at 3, positive 3, plus negative 9,8, and my time is what I'm interested in. So the time turns out to be equal to 1,36 seconds. And then sketch an acceleration time graph for this release pizza box. So it's acceleration, meters per second squared. Obviously, you give all your headings and things like that. And the acceleration, take upwards as positive, which means downwards has to be negative. So I have to go negative 9,8. And for the whole journey, that acceleration does not change at all. It is a flat line. And those are your key values. And if you want, you can put in the time. Sorry, I suppose that's a bit too much of a line there. There we go. And you can say that that is 1,36 seconds.